Okay, so as we discussed just above, what we're trying to do is that when we draw a sample from a certain population, the very first thing to do is to determine what distribution should we use to describe our statistics, like the sample mean x bar, sample variance s square, and so on and so forth. In our previous discussion just now in the second video, basically state, well, if your population distribution is a normal distribution, then what happens to x bar, what happens to s squared, and if you have two distributions or two populations we're drawing a sample from, what happens to their um, variances. Okay, so in this part, let's look at another commonly used or commonly seen scenario. That is, what if we're sampling from a Bernoulli distribution? This means we're drawing this xi's, and xi will be a Bernoulli random variable. Each one of them is a Bernoulli random variable. And Bernoulli random variable means you observe this sample take value 1 with certain probability p and takes value 0 with probability 1 minus p. This is how we define a Bernoulli random variable, Bernoulli distribution. And this is going to be the population distribution or the distribution for all the xi's we're looking at. So, if this is the case, now we're drawing a sample, and a sample will contain a total of n of these Bernoulli random variables. They are independent and identically distributed. So how do we deal with this? Well, as before, we know x bar is defined as this average of all of them. While the distribution of x bar is unknown, another random variable can be relatively studied. So if we'll introduce a new random variable, let me call it x, and let me define it x1 plus x2 plus all xn's without dividing the summation to n, just a simple summation of all. Then what we have? Then it's not difficult to figure out that x is actually a binomial random variable with parameter n and p. Okay? So binomial random variable is the number when you toss the coin for n times, each time you have probability p to see heads, and the binomial random variable will be the total number of heads you see out of the n tosses. Now what we have is we have a sample. The sample has a total of n individuals, and since each of them take value 1 or 0, when you add up all of them, of course all the zeros won't come into the summation, and all the ones will be added up. And of course the summation is just equal to the total number of ones or successes in and in a sample. Okay. So this is what we have. And because the distribution of x is given, of course the distribution of x bar can be calculated. It is not as pretty as the binomial distribution, but it can be easily sorted out. So if we, let's say, want to characterize the probability that x bar, the sample mean, is less than a certain number, this will be our cumulative distribution function. Because x and x bar, the only difference is this n in the denominator. So this probability should be just equal to the probability that x, our binomial random variable, is less than or equal to NA. These two events are equivalent, and of course the corresponding probability to measure the likelihood of the event should also be the same. And for the second one, since it's a binomial random variable, we know how this should be done, right? We just take the summation from 0 to an. So if an is an integer is fine. If it's not an integer, we can take the floor. And n is k, p to the power k. We need so many of them, and 1 minus p raised to the power n minus k. Okay. So this will be the case that we'll be looking at. Now, for binomial distribution, if let's say we want to calculate the mean of our x bar, what should be equal to? Well, as what we have discussed earlier above, x bar is an unbiased estimator, so the mean of the x bar is actually equal to the population mean. And the population mean is defined as the mean of my random variable x size. It is equal to what? It's the weighted average. So take value 1 with probability p, take value 0 with probability 1 minus p, and of course it's going to be equal to p, which is actually equal to what? This is the probability to see success, or you can view this as the proportion of individuals in the population that belongs to a certain category. For instance, the proportion of people who support a certain candidate in an election. And this is why we can use, okay, this is the math between a common practice that will look at the total number of people in a sample that support a candidate, divided into the total number of people you interviewed or surveyed, and you use the result to estimate the proportion of people in the population that support this candidate. So this is the probability theory or the statistics behind it. And this is when we are trying to calculate or sample from a Bernoulli distribution. So basically, it means your population is divided into two categories or two classes of individuals. Success, failure, 1 and 0, one candidate, another candidate, so on and so forth. So as long as you divide it into two, that falls into this particular case. And in the text, will also gives the case what happens when we're sampled from a Poisson distribution. The story is pretty much the same. We won't go into detail in this video. It is not as important as the normal distribution case and the binomial distribution case. So we're going to only focus on these two scenarios, sampling from normal distribution and sampling from binomial distribution. Okay. So this is about all the sampling distribution, probability distribution of the statistics. And next we're going to look at something called statistical inference. Before looking at statistical inference, maybe let's just revisit the parameter estimation again. During Tuesday's lecture, I mentioned when we talk about estimation, there are two types of estimation. One is called point estimation, the other is called interval estimation. So point estimation is going to be very simple, and we actually have touched upon that um, for a while already. Okay, um, so it's going to look like the following: point estimation. The goal is to use or to define the statistic such that you can use that statistic to calculate, to do a certain calculation when you collect the data and use that calculated statistic to estimate a certain population parameter. This is what we have discussed before. We discussed we can use XBAR to estimate the population mean mu. We can use sample variance to estimate the sample variance. Okay. These two are very natural, and we discussed above. They're called unbiased distribution, and we discussed why. Sometimes when some of the probability theory are very intuitive, some of them are not as straightforward as that. So the one we're going to discuss right now is a little counterintuitive, is that how to estimate sample standard deviation, sigma. Well, you can say, well, it's simple. We just take the square root of your sample standard deviation, so like this. But it turns out that this is not an unbiased estimator of sigma. Well, this is the bad news. The good news is, well, it's not going to be that dramatic because we can usually do a little tweak. Okay. So what we're going to do is that we're going to use S, the sample standard deviation, and divide this into a constant C4, where the C4 is a constant. Okay. And it depends on your sample size and so on. And there's a table in the appendix that can give how the C4 can be calculated. In the book, it also includes the formula to calculate the C4. It relates to the gamma function, but the table has a summary of how the value of C4. This is one way to do the calculation. Another way to calculate is to use this, R over D2. R is another statistic, and R is defined as the maximum value in your sample minus the minimum value of your sample, or in other words, it's the range of the sample data. And again, D2 is a constant and depends on the sample size. And also, the one of the appendix table provides you a list of um, values for D2 for different sample sizes. Yeah. So, for instance, if you're working on a problem and you're trying to do some calculation, try to estimate the sample variance, and try to estimate the population mean, population variance, population standard deviation, make sure you use the correct formula. Some of them, as we mentioned, very straightforward when it comes to sample mean and sample variance. Some of them may not be that straightforward. Okay. especially the sample standard deviation, which if we simply take the square root of the sample variance, is not an unbiased estimator. We have to do a certain modification to make it unbiased, and this is it. Okay, so I'll stop the video here, and then we'll have a new video on statistical theories.